Hey guys, today I'll be teaching assigned cookies, lead code number 445. It is an easy question, but this will be my first ever time covering a greedy pattern on this channel, and I'll show you, I'll explain what greedy is, and then I will show the approach for this question in particular. Uh, Greedy is all about, so when you have, let's say, two numbers, right? And you want to decide, okay, let's say you have three numbers and you want to decide the minimum of the three. So you would look at 1 and 2, then you would look at 2 and 3, and then you will look at 1 and 3, right? But greedy is exactly the same thing. So when you're given a very big, let's say, array or anything, and you have to find the minimum, you make like these small minute choices, like comparing 1 and 2 elements or comparing 2 and 3 elements, to try and get a locally optimal solution. That's what they call it, a locally optimal, in the sense that it is small in the grand scheme of things, but this small optimization that you've done will apply to the larger array. So let's say a one way, I mean, if you've learned about graphs, a greedy example for that is it's called the Prim's algorithm. You can look into it. Off the top of my head, it's the Prim's algorithm, in that the algorithm is just picking the lowest weights in the graph, right? So this is one very good greedy approach. It's also formally covered. Besides that, you could look into knapsack problems. Then there's also Huffman coding. Huffman coding is about like always picking two minimum elements, and then always doing that such that your encoding comes out to be like a minimizing the amount of bits that you essentially need, like in file compressions and stuff. So minimize bytes. And now I'll talk about the question itself. So what we are told is there is a greed factor on every child. I'll write up the first example itself, 1, 2, 3. This means that child 1 has a greed factor of 1. He will consume one cookie, essentially, okay? And S over here, S is the storage that we have, okay? And the storage as in the size of the cookie. So if we matched 1 to 1, the kid would be happy, okay? If we gave 2 even, I mean, usually there's no need for this. Usually you have greater than or equal to. So if we had 2, in both the examples, what I mean by you don't need it is in both the examples, they don't really illustrate this, but 1 would also be happy being matched up with 2 on this end. So if we had a 2 magically here, 2 would also be happy being eaten by child number 1, right? Child number 1 would be more than happy to get a bigger size of cookie, but a cookie size smaller than the one he needs, he'll be angry about it. Essentially, it's just they're pairing up the size of the cookie and the kid's greed, right? And that's why they've given the condition as well. The size must be greater than or equal to the greed of the child. Now, the first thing that should pop into your head when you look at the example is, what if we had a pointer and a pointer here? It's kind of like the merging two sorted lists, let's say, that kind of question, where you had 1, 3, 5, and you had 2, 6, 7. What you would do is, instead of doing like a plus, that's not allowed, you would have this, and then you would do this. So you would essentially keep a 2-pointer approach, where you would have 1 and 2. You would say 1 is smaller, and then you would move your left pointer ahead, you would have 2 come out, and then you would move 3, and then you would see, okay, 3 is smaller, so move that, 6, so you would eventually get up 1 3 5 6 7, right? And it's the same approach with this one. If you have 1 2 3 and you have 1 1 over here, you can have 2 pointers on this, and you see that 1 is greater than or equal to 1. You say, okay, well, if it is greater than or equal to 1, I'm very happy, I'll just move both of them ahead, right? Because you can reuse the same cookie, and since the child has been fed, he won't bother you again. So now the next comparison would be, is 1 greater than or equal to 2? Which it isn't, right? Which it isn't. So if we go to 3 as well, 1 is greater than or equal to 3 is also false. So we can see that this cookie would be left over because both of these elements are greater than that, and we could only make one match, right? One match, and that's exactly the answer as well, one match. Now I'll show another example, 1 2. After this I'll write the code, but just so you, I would encourage you to, as I've explained this, write out the code already. It will help you understand the approach a bit more as well. You'll see a bit of edge cases, but 1 2 1 2 3, right? And we have a pointer over here, we have a pointer over there. We are happy to match these two, so yep, they would go off, and then we would have this and this. We're happy to match these two as well, no worries. Cut this out, and then we will come here, and we would see, well, 3 really, there's 3 cookie, but nobody wants to eat it, so it will just be left off as is. But what matters is we made 2 matches, which is the answer as well. So essentially the way we actually do this is essentially just like the same thing that we did with 2 sorted arrays. We just sort both of the lists. And why do we do this? Well, because we want to always increment the pointer to a point where it's greater than what it was. So if you've done 2 sum when we had, let's say, 3 9 and 11, your first thing would come out to be 14, right? But if you wanted to maximize the sum, you would bring your left pointer over always, so you would get 9 plus 11 20. And if you wanted to minimize it, you would bring out your right pointer down, so you would do 3 plus 9 12, right? So that's how you minimize and maximize your sum in that particular, like given a sorted array. And then counter, like I said, 0. Now when do we actually just run this? Like I was shown here, if there's more cookies than what the child want to eat, then we don't really care, right, about the third cookie being left over, because we need to make matches. That's what we're concerned with. And it's the same way around. If the child is, well, if there's more children than the amount of cookies, then we can't give every child a cookie, so some kids will be left alone. So we can't really do anything about that. But what we do care about is matches, right? So we will base it only off of the matches. So if you do while I is less than length of our greed, j is less than length of our size, if they satisfy the condition. So the condition in the question, literally, if you just copy that over, if we do have a match, like I said, we would increment both pointers. We would say a match has formed. But in the case that it wasn't, well, we have to increase our size, right? Because now the kids' greed is more, so we have to try and increase our size. So that's what we'll do. We'll increase our size. But there was no match, so we won't increase our counter. And at the end, we will just return counter. That's it. That's all there is to this question. So you have 2 sorted lists, and then all you're doing is just doing 2 pointers approach. I have shown 2 sum 2. This is a very good question to go and do 2 sum 2 after this. It shows you the way you would So sorting is usually something that greedy also does have. I forgot to mention this, but most of the times when you do a greedy approach, you would have like an order that you would pick from, right? Because you have to make these local optimizations, but you also have to apply to the full grand scheme, right? So these local optimizations, you would have like a key or like whatever you have, like a list. You would have any data structure holding your thing, and then you would, well, operate on a part of it, then you would operate on the next part, then the third part, and so on. So usually you deal with things like that are sorted in a priority, uh, anything that's giving a specific ordering. That's why Prim's algorithm works really well. uh, it essentially is, you could think of a min heap because you would always keep the minimum element on top, and if it forms a cycle you wouldn't pick it. So it's essentially just